Buddy, it's Jordan here, and welcome back to my Rstudio YouTube series. And in previous sessions, I've done quite a lot of focus on statistical models, ANOVA, LM, and both of those are what we call parametric tests, which means that to be confident in them, we need normality of the residuals and equal variances of the residuals. Like I said in a previous video, if you don't have those assumptions or you're missing at least one of them, you can do Kruskal-Wallis or other non-parametric tests like Mann-Whitney. I also touched on Tukey tests in a previous video, and Tukey tests are what follows an ANOVA. Okay, so it's post-hoc pairwise comparisons when you have shown by ANOVA that your assumptions are met. Okay, so you've got those assumptions being met of normality and equal variances, and then you can successfully run a Tukey test and be confident in your Tukey test. You kind of really have to run post-hoc. I don't know if so many people put such of an emphasis on it, but you really want to compare every pair, right? All the levels against each other. Okay, let's just talk a little bit about levels so we're on the same page with this. And I'm going to go back to my old favourite MT cars. By now you'll be familiar with some of the data frames I keep on using again and again and again. Okay guys, so imagine we wanted to make an ANOVA that looks at the effect of CYL on MPG, miles per gallon. So this CYL column is the number of cylinders of these cars, and this miles per gallon, MPG, is obviously self-explanatory, miles per gallon that the car can go. And the different names of the cars are listed here. The number of cylinders varies between 4 and 8, and there's only 4, 6, and 8, right? Those 4, 6, and 8 are levels. And we'd want to compare in a post-hoc 4 versus 6, 6 versus 8, 4 versus 8. Okay? You're not going to get those pairs from just the summary of an ANOVA, so you have to do a Tukey post-hoc test. A lot of people feel like Tukey is the main or the only post-hoc test that you can do, but that's not right, because as I explained, you want to do another kind of post-hoc test if you have violations of assumptions. And one that you can do when you have non-parametric results is called Dunn's. Alright then. So let's see what Google will tell us about this. Tukey's honest significant difference, that's why it's called Tukey HSD test, and Dunn's test are both post-hoc procedures used to compare groups against after a significant omnibus test, like ANOVA, but they are used, or Kruskal-Wallis if you're doing non-parametric, but they are used in different scenarios and have different responses to violations of assumptions. Tukey HSD is a parametric test suitable for ANOVA, while Dunn's test is a non-parametric test typically used after a Kruskal-Wallis test. And like I said, if you have a violation of normality of your residuals or equal variances of your residuals, consider using Dunn's, but there are other ones as well for non-parametric post-hoc. And today we'll just look at Dunn's and Tukey as well. Okay, so let's go back, and I just want to say at this point that for stats questions, Google's actually really useful. I just, these days, if I have any questions, I'll type in keywords related to my question, okay? This wasn't a full question, but some of the keywords I was interested in was Tukey, Dunn's, and violations. And the answers are actually pretty comprehensive, eh? That's changed in the last few years. So the next thing, in order to give an example of Dunn's in action and Tukey in action, we want to identify and create some models that give where the assumptions are being met and where they're being violated. before we then go on to do the post-hoc tests. In a previous session, I think it was the last one, I talked about the mammal sleep data frame. And mammal sleep data frame is actually found in several different libraries. The one that we used last time was called Faraway. So mammal sleep was a data frame in Faraway. But it's also found in various, I wonder if it's the same. It might be the same or it might be slightly different. It's found in various different formats in other libraries as well. So here it's the mice library. Okay. And we can get a lot of information just, from this rdocumentation.org website. This is one of the best websites, just for telling you about all different codes, packages, and data frames. Everything's abbreviated in this data frame. Okay, so going back to I've already brought this data frame up. Okay, it's got BW, BRW, SWS, PS, TS, MLS, GT, PI, SEI, and ODI. To give more information about it, it's all information about how many hours, per day that animals are showing, these ones here, African elephant, cow, donkey, etc., are sleeping. TS is total hours per day that it's sleeping. And then it's also got pretty cool stuff about how many hours per day it's not dreaming, but is sleeping but not dreaming. And then how many hours a day it's sleeping and dreaming. Then it's got information about its maximum lifespan. And let's move on to these three, PI, SEI, ODI, all the ones that end in I. This is some measurement of the risk to the animal. So these three columns talk about the likelihood of the animal being predated. Where 1 is least likely to be preyed upon and 5 is most likely to be preyed upon. This is similar SEI, but this is kind of information about if it's protected when it's sleeping, which then these two numbers here go into this final column, which is an overall danger index. So it's the risk that an animal faces of being attacked or eaten. And 1, again, is least danger from other animals, and 5 is most danger from other animals. So now we understand a lot about what each column contains, much more than we ever would have just by looking at the names of the columns, where we would have understood practically nothing. So let's pay attention already to the final column, which is its overall risk. 1 is less likely, let's see. 1 is least danger from other animals, 5 is most danger from other animals. Alright, cow, donkey, goat, they're all up in the 5s. And I was talking about this with a student the other day, and I realised that those are all pretty big herbivores. They're not really known for attacking other animals as much. So they have a high risk. And then you've got Arctic fox, big brown bat, cat. They are actually facing least danger from other animals, which is kind of cool. Then TS is total sleep. And what I thought was interesting about this is just the huge range in the number of hours that these animals are sleeping, right? Little brown bat is sleeping about 20 of the 24 hours in a day, whereas the roe deer is 2.6. You've also got things like monkeys up here sleeping a lot. Water opossum, 19.4. So there's a lot of sleepers in there. And I believe man's in here as well. Let's scroll down. Yeah, man. So they've got 8 hours for man, which is actually pretty accurate because that's close to what we're supposed to be doing. Again, that's the total sleep column. Total sleep hours per day. very, very interesting questions arise about, you know, how they measure, for example, dreaming and non-dreaming, but apparently animals dream, and that's pretty cool. So I'm not sure if how long this is going to take, and I'll pause the video and just skip it and edit it if it takes too long. But what we want to do now is use this data frame to create a model that results in assumptions being met, okay, from ANOVA, and then a model with assumptions being violated from ANOVA. So these are libraries that I have already loaded. We won't use them all until a bit later on. Okay, some of this is plotting stuff, but they're there anyway, and I always load them at the top. Okay, and I always load option SciPen equals 999 for the stats results. Okay, next, let's create something here. We generally would, I think let's look at the total number of hours of sleep and see how that varies with some of the other ones, okay? Let's see how it varies with body weight first. So TS squiggly line BW. Alright, so we run that. And then we do, firstly, well, this isn't crucial right now, but we'll just see if there is a significant effect. Yeah, there is. So we know from this already, being less than 0.05 plus a star, that there is an effect of body weight on the total number of hours sleep. That wasn't even a crucial point here. The crucial point is the residuals. And you might remember I do this because I want to show 4 residual plots at the same time. These residual plots will tell us something about the variances and normality of the residuals. Okay, so we just go plot and then the name of the model. Test. Okay, so these are the plots you've seen before. If the residuals, which are these circles, and residuals are differences between observations and predictions, if they all fall onto the dashed diagonal line in the background, that's normality. These, we're kind of looking for flat red lines, so I'm not sure about this. But let's do further analysis of this. I wouldn't come to any conclusions based on these graphs. What I'd do is load a couple of other libraries, okay, which can give us p-values that relate to normality and equal variances. And so those libraries are nortest, this one here. If you don't have these libraries, whenever you run library nortest, it will just say error not found. You go here, and you search for it here. Okay, I've got it, so no problem. And then it should be turned on either in here by the buttons or here with the library code. Okay, and then the other one, this is for equal variances test, is called car. Okay, let's explore these assumptions more by doing this. Okay, so what we want to do is we want to put AD test, yeah, add.test, okay, brackets residuals. We don't need to write the word residuals for the car test for the equal variances. This is a normality test, and for this one you've got to put the word residuals first, and then just the name of the model, which is test, okay. So this is our normality test, and I'll leave a note of this. I'll also leave a note here saying residual plots. Okay, then we run this and we get a p-value, and this p-value is good. Okay, so let's talk a little bit about that p-value there. That is p-value of 0.505, and that's good, okay? And the reason why it's good is because normality is the normality assumption is met at p above 0.05. Okay, less than 0.05 would be non-normal. So that p-value here that we get from the Anderson-Darling normality test is kind of consistent with the shape of the residual distribution here. Okay, most of the residuals fall onto the dashed line in the background, and so both of those give us confidence in the normality assumption. Okay, what about equal variances, the other main assumption of ANOVA, AOV? Alright, I'll just note at this point that in terms of normality tests and equal variance tests, there's a few different ones. We use the Anderson-Darling one. There's also one called Kolmogorov-Smirnov and another one called Shapiro-Wilk. They are a little bit different in their maths behind the scenes, and so you might get slightly different results. Just check online about which one is right for your data. I'm going to do something here prior to doing the equal variance test. What I'm going to do is just turn this into a factor, okay, and check how it affects the results. So at the moment, BW, the body weight, is numeric, and we can just see with and without that. Okay, now it's 0.412. With the factor, it's 0.412 for the effect of BW on TS. Now it's 0.019, and this is actually a good important lesson. So this is probably not a great column to choose for this, because to test the variance assumption, we need this predictor to be a factor, okay? And if you don't have it as a factor, it gives an error. So that's why in this case, when they show you how to use the Levene's test in the car library, they put CIL in empty cars as a factor. It's used for groups, right? So this might not be the best data set to work with, where we're going to use the BW, which is clearly supposed to be numeric, as a predictor. Let's just take, at this point, a different one, okay? Let's take the ODI and have a look at that. I'm going to turn this into a factor now. You can either turn it into a factor there within the code, or you can turn it into a factor beforehand in the data frame. But this looks really good as well, and this looks good. So we might be onto a winner now, for sure. Okay, I'm going to check so remember, this is the effect of ODI, the risk to the animal, on the total number of hours sleep. And you'd be assuming that if it's got a lower risk, it can sleep better at night. Let's check the Anderson-Darling. Oh, we've got a great p-value here as well. So we got kind of lucky that we didn't have to spend too much time adjusting the model and choosing different variables. Let's check the Levene's test now. Okay, and I'm not sure if you can turn it into a factor within the Levene's test, or it needs to be done before, but we'll find out. Okay, so you start typing Levene, and this one doesn't work anymore. Defunct functions in the car package. This one works. Levene test. Alright then. This is interesting because when you just put Levene test and then the name of the model, it doesn't work. Okay? Which is strange. So what we've got to do is you've got to copy this part again. Okay, paste it here and turn the AOV into that word there, Levene test. Okay, and we'll call this one variance test. Alright, cool. That seemed to work, no errors. So this was a little bit more complex than this, where we just had to put the name of the model. Now we've got to write out the model again. Summary variance test. Okay, so it's not summary variance test. I always get confused whether you have to put summary or not. You just have to write variance test. Okay, we have a violation here because this is lower than 0.05. And that means, yep, so that means less than 0.05 means that variances are not equal, which is a shame. So now I'll take a wee pause, come back, and find one where both assumptions are met. We'll use this one to do a Dunn's test on the Kruskal-Wallis because of the violation of the variance assumption. Alright. Guys, so I took a little pause and I tried to go through the other columns in mammal sleep, and then I realised that there was only really 3 that could realistically be used as factor predictors. Okay, that's all the ones that end in I, the risk columns. All of these are kind of supposed to be numeric. This one, and this one all created a violation of one of the assumptions. So it was like we don't have both assumptions being met in order to be happy with our ANOVA and then to do a Tukey test. I then went back to my default favourite, MT cars, and I chose one of the columns that can be treated as factors in that. I tried all of these, and actually gear, okay, produces the assumptions being met, allows the assumptions to be met, normality and equal variances. So basically the model would be miles per gallon, squiggly line, factor gear. Okay, looking at the effect of gear on the miles per gallon. I can run the normality test for this, and we've got 0.2461. Okay, normality is met. The Levene's test, and note up here I called it a name and then wrote its name afterwards. You don't have to do that actually. You can just not call it anything and start off with Levene's test. Exactly the same as what we wrote in the ANOVA. And we've got a very similar p-value to the normality p-value, the Anderson-Darling p-value. Okay, and that says that the equal variances is met as well. So this is a model that you can use ANOVA for and be happy with the ANOVA. Let's then try to understand what is going on in the model just by summarising the ANOVA itself. And we've got this p-value here. A lot of people get confused with this p-value and comparing it with these p-values, okay? Because here, this is a significant effect. And that's shown by the number of stars and the very low p-value, okay? Significant effect. So whereas in the normality test and the equal variances test, we kind of wanted it to be above 0.05, here, I'm not saying we want it to be less than 0.05, but less than 0.05 is a significant result, okay? So don't get confused with which side of the 0.05 you're on. Okay, so now we know that our test is suitable for Kruskal-Wallis, Posthoc, and their test 2 is suitable for a Tukey test. Alright, let me start off with the Tukey test then. Okay, so we'll do a Tukey test first. And to talk about Tukey test, okay, we're going to be using this one. And another one that is always automatically loaded when you start R called stats. Okay, so I don't have it in the list here because it always starts by itself. And it's pretty easy. You just write Tukey HSD. We remembered what HSD is from Google. Okay, and you just write the name of the model, and that one's test 2. Okay, you put a comma here, and you write the name of this thing here, okay, this predictor, factor gear, equals quotation marks Tukey. Okay, it doesn't like, let me see what happens if you put this in here. It doesn't like us doing the factor within this Tukey test. Oh, it does. You just have to put that in quotation marks. Okay then, so this shows pairwise for the Tukey pairs, for the pairs. It compares 4 to 3, 5 to 3, 5 to 4. These are the different gears for the different cars, okay? And we get confidence intervals, the lower and upper of the confidence interval, and a p-value. So this p-value is above 0.05. That is non-significant, so this works the same as the ANOVA, okay? You want it to be less than 0.05 to be significant. This one's not either, because it's above 0.05. This one is. So there's a significant difference in the response, miles per gallon, between 4 gears and 3 gears. Okay, it gets a bit more interesting when you do plot. We're going to name it first. Well, you can name it or you can just copy it. In fact, I won't name it, I'll just copy it. Put that in brackets. Okay, and you see a graph here, and that graph is of the confidence intervals. And basically, when the line does not touch the middle vertical line, that's significant. Okay, that's a significant difference in the mean, miles per gallon. Again, that corresponds to gear 4 and 3. Here it touches the middle line, and here it touches the middle line. Those are consistent with the p-values here and here, which are non-significant. Okay, so these are not significantly different means. And that is probably all I'm going to say for that, except from there's another library called multcomp. Okay, and let's just do a multcomp Tukey plot search on Google. This can be used as well, which is actually, it's nicer because you can add colors. You'll remember what I said about touching the middle line is non-significant, and when it does not touch, that's significant difference. And this library allows you to plot the significant Tukey results in different colors, whatever color you like. Here they've chose red. So it's not essential, and if you try and publish, they might not like it anyway. Plus, it doesn't really tell you too much that a description won't. Okay, but that's possible. Now let's do Dunn's test on the test model. So that is being done because we have this the test model that we created, test here, had a violation in the assumption of equal variances. So that was using this ODI to predict total sleep. We had a problem there. And so what we can do is we can just firstly use this library, FSA. You're going to need that for this, Dunn's test. Okay, and then you copy the code for Levene's test, you paste it here, and you turn this into Dunn's test. Dunn test, yeah. Okay, we change out these for TS, and we change out this for ODI, and we write here the name of that data frame, mammal sleep. Okay, so let's see what happens now. Okay, it did work. The reason I'm using this library is because the Dunn test allows you to do two things in one. Okay, it does the Kruskal-Wallis for you. It shows the Kruskal-Wallis, it shows all the results in the console, and it shows the Kruskal-Wallis result first. Okay, and a p-value of 0, i.e. significant. Unfortunately, that's not giving us like all the decimals here, but if it says 0, that's a significant effect of ODI on the TS, total number of hours sleep. Okay, then you get down here and this shows you all the individual comparisons, just like we got in this line here for Tukey. Okay, apparently nothing happened when I did a plot of this. Unfortunately, it didn't, like it did in the Tukey test. But don't worry, okay, because Jordy always has a backup solution. And this is where I'm going to introduce you to a very nice little library called GG Simple Stats. GG Simple Stats. I've already loaded it above, but I wanted to draw attention to its name here. And it's one that I recommend you get. It's a little bit like the GG Stats plot and SGplot libraries that allow you to put stats results on a graph as well as the raw data, okay? But I like this one. And the reason I like this one is because it's built quite nice, and it allows you to, you know, produce a nice graph with the p-values without too many customizations. It does require ggplot code, so you need to already have ggplot code written to examine the effect of ODI on TS. But you should know by now how to do a ggplot from previous sessions, and I will just start one here. Okay, let's just do a scatter plot, the kind of go-to when you're just exploring data. Data equals mammal sleep, comma, AES, brackets, x equals factor ODI. And again, normally what I would do is I'd put ODI as a factor earlier, okay, right at the beginning with the $sign instead of here, but it works here, so you can do it here. And then we want y equals, which is going to be TS, okay. We don't need anything else for now, but we can make it look a little bit nicer in a second. Geom point is our second line. The second line of a ggplot is always about the type of graph. Plus, okay, and then you just, this is actually the code to show the p-values for the Kruskal-Wallis Dunn test. And if you start writing the word stat, okay, stat underscore, we do have a lot of different options here, but somewhere in the list is what you want, okay? I'm gonna now start writing stat underscore KW. It's this, stat underscore KW, all pairs done test. And you don't necessarily need to add anything else. That's what I really like about this. You can create or put statistical results on the graph without too much customizations. I would definitely not hand this in looking like this though, because it might be pretty basic. Okay, so these are the data being plotted here. You've got each different risk level, where 5 is most risk and 1 is least risk. And remember, the cows and stuff were up here, and then there was a bat here. These lines are for pairs are significantly different. So we've got this kind of like square, what do you call that? Square line or whatever. It's like, you know, phylogenetic tree kind of thing, but basically that exists between 1 and 5. So those pairs are significantly different in the mean TS, or in the TS. The same exists for 2 to 5, and the same exists for 3 to 5. But there isn't intermediate pairs are not significantly different. So what we can do when we have that is we can compare back with the results from this. And let's see. So this is a little table that shows, you know, 1 versus 2, the 2 versus 3, and the bottom number is the p-value, okay? So you notice that these ones here, 1 versus 2 is above 0.05, not significant, and there's no connecting line between those numbers. Same here. It's actually only the fifth, number 5 on the ODI, that has the stars on it. So that seems to match up pretty well with what our graph shows. We probably wouldn't want to leave it like that. I would probably at least do some sort of nicer theme dark maybe. And you might decide, actually that's not very nice, theme classic or theme pub R from the GG pub R library. You would definitely want to leave in a caption that these are the results from Dunn's pairwise comparisons, and you'd want to update your labels and stuff like this. Let me think. You could also very easily turn this into a box plot with just one word change. That might actually reveal more information. Yeah, I would say so. So because now you see the interquartile ranges of the data, and you importantly see the median lines. So these are the median lines, and it's these that are being compared in the Kruskal-Wallis. That's why this kind of box plot would be very suitable to show with Dunn's test results. Number 5, as you can see, okay, is way lower than the other ones. If you have a risk level in ODI, which encompasses, you know, like if you go back to the data frame, encompasses the danger from the sleep exposure index and the predation index. If you've got a 5, you've got the most danger. And sadly for those animals with the number 5, they don't sleep very much. So I think I might call it there. Let's just for fun make the graph a little bit more colorful. We're going to do factor ODI again. We don't need this because it's double coding, but I've just colored the factors by different colors here. And if you have any questions about anything I've done today, please leave them in the comments. Hopefully now you understand how you'd go about deciding whether the Tukey test or the Dunn's Posthoc test are suitable in your case. Don't necessarily just use one or the other. Check your residuals. Use nortest, Anderson-Darling, or other normality tests. Use Levene's test, and based on those numbers, if they are above 0.05 or below 0.05, you can decide which posthoc is correct to use. I wish you the best, and I hope you have a great day. Bye.